All right, so this is stoichiometry in solution chemistry, and we are going to manipulate math that we have done before, basically. So we've already done stoichiometry. You've already solved for moles using C and V instead of mass and molar mass. So we're just going to look at it in a different way. And one of the things we're going to focus on, and again, this is really important for grade 12, is writing dissociation equations. So when you dissolve an ionic compound, you're going to form an aqueous solution. And ionic compounds can dissociate into ions in a solution. So if you're asked a question about dissociation, then you can assume that it's going to be soluble. Okay, so when you write a dissociation equation, you're going to start with the solid on the left, and it's going to make ions on the right. So normally when we write the formula for an ionic compound, the cation or the metal comes first, and the anion or the negative or the non-metal is second, because we always write in a chemical formula, whether it's ionic or covalent, we write the lower electronegativity element first. When you do this, sort of like adding in math, it doesn't really matter which one you write first, but most people will put the cation first because that's written first in the solids formula, and the anion second. So again, that's plus and minus. But the big thing when you do dissociation equations is to include the state. So the solid always goes on the left, and the ions on the right-hand side are aqueous. And that's going to be very, very important for the math that we do in grade 12. Okay? Oh, actually, this is on the next one. Sorry. So dissolving an ionic compound is represented by what we call a dissociation equation. So solid is always on the left, and the ions are on the right. And again, including when we get to grade 12. So you're going to receive marks, whether they're communication for format or actual marks, including in grade 12, that the solid's on the left and the two aqueous ions are on the right-hand side. It's always going to be two. There's only ever a cation and an anion in an ionic compound. Covalent compounds are things that are like glucose, let's say, C6H12O6, which has three elements. That does not dissociate, so we're not worried about that. Okay, so it's always going to be solid and then aqueous. When you make an aqueous solution, the water part is sort of what we say is understood. Technically, dissolving is not a chemical change, which means it's easy to reverse. So really, you could actually, if you want to include water, then you would have to put it on both sides, that is redundant. So we just put solid and then aqueous, and that takes care of that. Okay. So an aqueous solution, it's understood that means dissolved in water, as it has since the start, okay, of this course, right? We've already talked about that. Okay, so when you are asked to write dissociation equations, or if you're going to do a question like you can see in the second bullet point, you need to write your own dissociation equation to make sure and see what the coefficients are, because again, this section deals with stoichiometry. Okay, so I'll give you the formula of the solid, as you can see here. Could I ask you to crisscross and whatever? Yes, but that's not really the expectation in this section. So it's important how many of the ions are formed. So the crisscross rule and all that kind of stuff. So and that's an annoying mistake. So then it's just perpetrating the mistake can really affect your math. So I'll just give you the formula. Same thing in grade 12, to be honest. Okay, so the first one we have is barium oxide. So you write BaO, And the S splits apart, into barium and oxygen. So now we want to really emphasize that they are ions. And here's a really good case why. So people will be tempted to do this, but that is not true here because that is only true when it's oxygen gas. So that's why the solid and aqueous are so important to distinguish the state of matter you're talking about. And another thing that I really encourage you to do, and sometimes in grade 11 students get freaked out and they're like, I don't remember the charge, I don't know how to figure it out, but it will really, really help you be more successful when we do different quantitative analysis in grade 12, okay? So ions should have a charge. Which means that in this case, you either look at the column that they came from, you could uncross, but here that's a little difficult because their charges have been reduced. Okay, so you look, barium is a alkali earth metal, so it's in the second column on the periodic table, which means it's got a charge of 2. Whether you write 2 plus or plus 2, I don't care about that. Same thing with the oxygen. Okay, it's 2 minus. But one more time, when it's aqueous, that is not oxygen gas. That is not what we're talking about or what we're worried about. Okay? Same thing down here. So now we have lead iodide, lead 2 iodide. And this can be even more annoying because it almost looks like it should be I2, okay? But that's not what happens here. So we get lead ions, iodide ions. So try to think of it as ions, not as its elemental form. So I'm gonna uncross this 2. So this becomes 2 plus. Metals are always positive. And then the iodide is negative. And so now the part of this that deals with stoichiometry means that there are going to be 2 iodide ions. It becomes a coefficient. So that's going to be important later when we do stoichiometry. So the subscript in the ionic compound becomes the ion's coefficient, okay? But then what about this? So now this is a special case as well. Because now we kind of have 2 kinds of coefficients, right? We have the coefficient here on sodium, and then we have the coefficient on sulfate. But you have to remember, another thing to remember is about polyatomic ions. So even though there are 3 types of elements in this compound, there's only ever 2 ions, right? A positive ion and the negative ion. So if you struggle with the polyatomic ions, they're on the back of the periodic table. So sodium is an alkali metal. It's got a charge of 1 in the first column. Sulfate, if you don't remember what its charge is, which is completely fine because it's in that chart, it's negative 2. And then, of course, this 2 here goes out front for sodium. Let's just, I already used yellow. Let me get a different color. And we've also already looked at the fact that polyatomic ions don't split apart because we did like net and total ionic equations, right? So it's the same sort of principle as that, okay? So If it helps you to put brackets around them, even though we don't need them when you're not crisscrossing a charge, do it, okay? Whatever is going to make you successful. Okay, so another thing about this is that when you do this, you'll be given the formula of the solid always. There's always going to be one type of positive ion, one type of negative ion. And another thing too is that the solid's coefficient should be 1. And not should be 1 like if you balance it incorrectly, whatever. If you need to put a coefficient in front of it, then you've done something else wrong. Okay, so it should always be 1. Okay. So then in a question like this, if it was on an assignment or, real test exam, whatever, I would actually put write the dissociation equation for sodium sulfate. And then this would be like part B, if the whatever. So we've already done sodium sulfate up there. So that's why it's not like this here. And in your textbook in the homework, they might gloss over that. So make sure when you do these kinds of questions, you always need a dissociation equation. But if it's an assessment from me, I'll give you marks for it. Like it'll be explicit. Okay. So if the concentration of sodium sulfate is 0.45 molar, what is the concentration of sodium ions? Okay, so here is our dissociation equation. And we already have, we are given the concentration of sodium sulfate, and that's it. No moles, no liters, and nothing. However, because this value is already moles per liter, we can actually use it in a Stoic ratio. And we literally sometimes use the words molar concentration, right? So concentration is based on moles or calculated with moles. Then we can use it in a Stoic ratio. Okay, so we can go right ahead and do that. So I'm going to do it the same way as we would have done it before. So how many moles per liter of sodium, this is what we're asked for, sodium, over its coefficient of 2. And then we are given the concentration of the solid, and its coefficient is 1. Okay, so now when you cross multiply, I'm running out of room, sorry. X times 1 is 2 times 0.45. So the concentration is 0.9. Now, what you'll see, especially in grade 12, we are going to cheat at stoichiometry or streamline the stoichiometric process. So because the solid is always going to have a coefficient of 1, then anything with a coefficient of 1 is 0.45 or is the same. Okay. And then all you have to do is multiply by 2. However, this only works this is only really useful for these kinds of questions. So like in a normal question where you do stoichiometry, we're going to do one in a second with a weird mole amount. Then you'll want to use a full ratio. And one of the things about this is it's going to be like 1, 2, or 3. Maybe if you had a weird transition metal with a weird charge above 3, but those are the 3 columns that have like +1, +2, or +3 on the periodic table. So there really isn't that much variety in what the coefficients can be in these equations. Okay, so that is one way you can streamline it, but that will be more useful in grade 12. Okay, so let's do two more examples. So this one says calculate the concentration of chloride ions in a 26.5 gram sample of calcium chloride dissolved in 150 milliliters of water to make a solution. Okay, so first of all, I would give you this. I will tell you what calcium chloride is. So what I'm going to do, I'm going to do the work on the left and do my steps on the right so you can follow along, okay? So again, even though it doesn't explicitly say it, every single time you need a dissociation equation. And there are 2 sections in grade 12 where you need to write dissociation equations. So this skill will not be a loss, okay? So start with the solid on the left. 1 calcium ion. The subscript of 2 makes 2 chloride ions, okay? This time we're given grams. We never manipulate grams and convert them and compare them to others, so we have to convert it to moles first. Just like we would have in the last unit. Okay, you can't do stoichiometry without moles. So if you want to set it up the same way that we would have, 26.5 grams of calcium chloride, its molar mass is 110. And then the moles, so mass over molar mass, that's supposed to be an M, sorry, in case you forget, is 0.239 moles. Okay, so again, if you didn't even read any of the rest of the question, then that would certainly get you part marks. Okay, so always change grams into moles, just like we would have in the last unit. So now that we have moles, now we need to read the question carefully. So it's asking us for the concentration of chloride ions. Okay, so we are looking for the concentration of chloride, not calcium. So when we go and make our stoic ratio, we're going to use that coefficient. Sorry, I just didn't like the wording of that. Okay, so now we have, we found moles. I should label my steps here, number 2, number 1. So now we are going to convert it to moles of chloride. So how many moles of the chloride ion? Its coefficient is 2. And we have 0.239 moles of calcium chloride. Its coefficient is 1. Okay, so 1 times x, 2 times 0.239, very straightforward. Okay, so now again, we need to read the question carefully. What are we looking for? It wants us to change it into concentration. Using moles and volume, but remember it's moles per liter, so it has to be in liters. Kind of running out of room, so I'll write over there. So you divide by 1,000 to get to liters, or three decimal places in a conversion chart. 3.19 moles per liter. So again, you know, we often don't think about concentration necessarily for solids, but like I said, I make solutions all the time for your class, for other classes, and they have to have a certain strength, and again, have a certain strength even to make it precipitate. So, and that's the next step. So next year, we'll look at what concentrations will give a precipitate and which ones won't. Okay. So this question now is like a reaction. So we are given 25 milliliters of 0.085 moles per liter aqueous sodium sulfide is added to excess mercury 2 nitrate. What mass of sodium nitrate precipitates? So now we're going to convert it to mass. So this kind of question could be manipulated to, it does say excess here. You could be asked to find the limiting reagent. Because we are finding the mass of the precipitate, you could have to then do percent yield, but we're really going to keep it simple here. So we're just going to focus on solution stoichiometry. Okay, so sodium sulfide, this time we're given volume, which again has to be converted to liters. And we're given concentration. Okay, so we need moles, so calculate moles. Is C times V. And then we want to eventually find the mass of the solid. So they're not the same, so we have to convert it. So we're looking for how much sodium nitrate. Its coefficient is 2. We have sodium sulfide. Its coefficient is 1. So again, simple coefficients. And so now we're at moles, which is great, but then just again, read the question carefully. This time we're looking for mass and we're doing sodium nitrate. So I'm running out of room. I'm going to write up here. So now we're doing, I'll change the color. We're going to do mass. And we need the molar mass of sodium nitrate, which is 85. So sodium's 23, nitrate is 14, and 3 times 16 oxygens gives you 85. Okay, and that gives you grams. So take a look at the homework questions. There are a variety of types. Sometimes this section is actually poorly well done on the test. I don't know if it's because it seems like you've already done all this before, so people think it's easy and then they glance over it. But take a look at the questions, at least try one of each type so that you're good to go. Okay, thank you.